Hello friends, welcome to my channel. Let's have a look at the daily challenge problem 1061 again. Lexicographically smallest equivalent string. In this video, we're going to explain a solution based on traversal. First, I'll read through the problem statement, and then we do the analysis, and finally we share the code format. First, let's quickly look at the problem statement. We are given two strings, s1 and s2 of the same length, and a base string called base string. So we are required to return the lexicographically smallest equivalent string of the base string by using the equivalent relationships induced from s1 and s2. So here the equivalent characters follows from the corresponding index in S1 and S2. So same index characters in S1 and S2 are actually equivalent characters. So here we want to mention briefly that the equivalent relationship satisfies the following defined properties. So one is reflexivity, and the other is one is symmetry, and the other is transitivity. So with that said, we can look at these examples. For example, in example 1, so due to the corresponding character relations, so we know MP are equivalent characters AO, similarly KRS and EI. Then we scan the base string and replace the character with their corresponding equivalent smallest characters. Then the return will be MAKKEK. So here smallest is based on the string ordinal number, or the lexical order. So with that said, so we are going to directly go to the analysis, because this is a follow-up video, right? So as we mentioned that in a previous video, we explained a solution based on union find. So personally, I feel that the union find solution is very elegant to this problem. So here our plan is to solve and explain this problem based on graph traversal. So we solve the problem by locating the connected components, and then we find a representation of each connected component. So actually for this purpose, we could use either breadth-first search or depth-first search. So here, let's first walk through an example. So for example, if S1 is ABC and S2 is CDE and the base string is EED. So from S1 and S2, so we know that A and C are equivalent characters. Similarly, BD are equivalent characters and CE are equivalent characters. So here this double equal sign means that the two characters are equivalent. Therefore, we have two connected components. One is corresponding to A, C, and E, right? So this is represented by A, because A is the smallest one, lexicographically, right? So similarly, we have a BD. So this component, we are going to represent it by B. So therefore, if we replace the corresponding characters in the base string with the representations, so E is represented by A, and D is by B, so we're going to have AAB, right? Therefore, AAB is a lexical smallest string due to the equivalent relations. So with that said, so we know that a solution can be this. So we cast this problem into a graph induced by S1 and S2, and then so the connected components will correspond to the equivalent character sites, and then we can do the replacement to by the lexicographically smallest one in each connected component. Then it yields a solution. So with that said, we are ready to do the coding. So we are going to separate this coding into three parts. So the first part is to build a graph. So this is actually very routine. So we are going to introduce a graph variable. So we can use collections default dictionary. So here as a container will be the site. So you can use the vanilla dictionary, but this saves some lines of code. So here then we are going to iterate over S1 and S2 simultaneously. So we do this for AB in zip S1, S2. And then we know, so once their index are corresponding in S1 and S2, so the two characters A, B actually form a recurrent relation. So we regard this as a direct edge in the graph. So we're going to use this graph A and B, right? The add is a set method because graph A will be a set. Similarly, we're going to do this. So in other words, we're using a undirected graph or bidirectional graph. So this is the first part. For the second part, so we're going to write a find connected component function, right? Connect component. So this is actually very standard. So I'm going to use find connected component. So we're going to have a source node, and then we're going to return the set of nodes in the in other words, the connected component containing the source. So for this, I'm going to initialize a set. So we're going to return this thing as a set. So here I'm going to use collections deck. So we're going to initialize with the source. So here we can use this queue. So we can use it as a queue, or we can use it as a stack, depending on how we do the append and pop, right? First, I'm going to use it as a queue. In other words, it corresponds to breadth first search. So here is a standard while loop, while queue. So we have the node, so that is queue pop left, and then we're going to add this node to the result, or to the connect the component. And then what we're going to do is to check the neighbor. So for node in graph node, so this NB is for neighbor, right? So if neighbor not in the reference set yet, so we're going to do the append in the queue. So this way we append from the tail and then we pop from the left. So this is actually the queue behavior. So in other words, this code corresponds to a breadth first search. So we're going to return this result. So this is the second step. So the third step, so we're going to encode the problem logic, right? So this is also very simple standard. So here I'm going to use a reference set, so to avoid repetition. And then we're going to make a table, right? So for each character in the base string, so we're going to find its equivalent smallest character. So for this, we're going to use iteration, right? For character in base string. What we are going to do is to check if the character inside the graph or not. If character not in graph, so we are going to do this. The table character will be itself. Otherwise, so we are going to find the representation in the corresponding connected components, and then do the join. If character not in reference. If in reference, it means that we have done the assignment of the table. So for this, let's first find the connected component. So I'm going to copy this function signature. So here the source should be changed to be the character, right? And then we are going to first union this reference set, so that we do not need to repeat traverse the characters connected in this contained in this connected component. And then we are going to add a representation or delegate. So this will be the sorted, so the component, then we find the first one, right? And then what we're going to do is for character in the connected component, so we're going to assign this character to be the delegate. So with that said, we are done the identification of each character in the base string with its representations. So actually we just need to do for the unique characters. So this may save some time. So let's first keep this and then first finish this, and then we make some comments. So we're going to return. So here I'm going to use the string join method, and then we're going to use a list comprehension. So we're going to check table character. So for character in base string. So for now we are ready to do a test. So let's first do some test. So here set. So result at this node, right? So yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the test cases. So now we are ready to make some comments. First, when we do the assignment, we can just use this set, right? So in other words, we just need to do this for each unique characters. Let's check this again. Yeah, this passes all the cases. This is the one comment. Second comment is that here we are doing pop left and append from the tail. So this corresponding to using the queue variable as a queue. So now if we choose this to be pop, just pop from the tail and append from the tail, this corresponds to using queue as a stack. This function then corresponds to depth first search. Let's also do the test. Yeah, with that said, I guess that's about it for this specific problem. So in this video, following the previous solution or video on UniFind, we explained the solution using graph traversal. So here there are 3 steps. So we first build graph, and then we write a function to find connected components, and then we make a table and then do the replacement to get the lexicographically smallest string for the base string. So with that said, I guess that's about it. You're welcome to check out our playlist or channel for more problems or more analysis. So actually, as last minute comment, it's actually good to do the time complexity analysis for this problem. So here, this is the main time consumed. So actually, the time consumed for this kind of operation in the for loop in total is this n log n minus n times the entropy of the corresponding distribution. So this distribution actually is P, corresponds to this probability distribution P2 up to PMC, where n is the total nodes, and m is the number of clusters or connected components, and the pi is ni divided by n. So in other words, the number of nodes in each connected component divided by all the unique nodes. So this pi's sum together will be 1. It forms a probability distribution. So for each of the connected component, we need to do one sort. So the sort is an ni log ni operation, time operation. Then if you sum and you do some simple math, you are going to arrive at n log n minus n times the entropy of the corresponding probability distribution induced by the cluster sizes. So with that said, I guess that's about it for this video. Thank you.